We're looking at a paper today titled Whole Cross-Sectional Human Ultrasound Tomography. It's by David C. Garrett, Jinhua Xu, and the team over at Caltech's Optical Imaging Laboratory.
Yeah, and it's an incredibly exciting one.
Right. So to give you the core insights straight away, traditional ultrasound, it relies on those squishy handheld probes. You get this tiny little field of view. But this paper introduces a 60 centimeter, 512 sensor acoustic ring.
Which is massive.
Exactly. It generates these MRI-style two-dimensional cross-sections of the entire human abdomen, and it just takes a 10-second breath hold in a water tank. It uses completely safe sound waves, maps 3 distinct acoustic properties all at once, and totally bypasses the old problem of ultrasound just, being completely blocked by bone and air.
It really is a massive leap forward.
Yeah. So welcome to AI Paper Slop. If you're an AI researcher or an ML engineer tuning in, you might be wondering why we're focusing on a medical engineering paper today.
I mean, it's a fair question. It sounds like pure hardware.
It does. But while the domain is medical, the brilliance is really in the signal processing and honestly, the huge implications for the data pipelines you guys work with every day.
Because the bottleneck for AI healthcare right now isn't really the model architecture?
No, not at all. It's the lack of high-quality, continuous, non-radioactive internal data.
Right. And it's funny, you actually see this convergence happening everywhere. I mean, even Midjourney, the AI image generation company, they're apparently working on hardware for scanning physical bodies using sound.
Wait, really? Midjourney?
Yeah, it's wild context, but it just shows that sound is becoming this massive new frontier for high-fidelity spatial data. And this Caltech paper is basically the blueprint for how we're going to get that data out of the human body.
That's super interesting. Okay, so let's set the stage. The current state of ultrasound is, well, it's kind of primitive when you really look at it.
Oh, totally. It's incredibly bottlenecked by the physical operator.
Right. Imagine you're trying to understand the layout of a massive pitch black room, but you're forced to look through this tiny peephole with a little pen light.
That's a great analogy.
You only see the sliver of the room that the beam hits, and you have to mentally stitch the entire space together from these tiny flashes. That is essentially what modern medical ultrasound is.
Yeah, because you have a technician holding a small probe, and to even get a signal, they have to physically press it into your skin.
Which actually causes tissue distortion, right? Like, just by pressing down, you're mechanically warping the exact anatomical structure you're trying to measure.
Exactly. You are literally altering the data by collecting it. And because you only get that narrow peephole view, the interpretation becomes super subjective.
Right, like two different technicians might angle the probe just a millimeter differently.
And suddenly they get completely different readings on the size of a lesion.
Right. So what this Caltech paper proposes is shifting away from that subjective, physically distorted imagery to something objective and spatially complete.
But obviously the big question is, if full-body scanning is so great, why hasn't it been done with sound before?
Yeah, we've had ultrasound for decades. Why haven't we just made a bigger probe?
Well, physicists call it the acoustic barrier. Specifically, it's this thing called acoustic impedance mismatch.
Which acts like a brick wall inside the human body.
Pretty much. So when sound waves travel through tissue, they need a relatively consistent density to keep moving forward. The energy transfers from molecule to molecule.
But when it hits a sudden change in density, like an impedance mismatch, it acts like light hitting a mirror.
Exactly. So if the sound wave is moving through soft liver tissue and it suddenly hits a rib bone or, an air pocket in the stomach,
the density changes so fast that the sound just can't penetrate. It scatters or reflects almost entirely back.
Right. And because the sound bounces back, everything behind that bone or air pocket is just left in the acoustic dark.
It creates these massive shadows over the deep organs, which is why trying to shoot a sound wave all the way through a human torso was considered basically impossible.
Until now.
Right. Let's talk about the hardware leap here. They built a custom 60-centimeter diameter array, big enough for an adult torso. And inside this ring, they have 512 receiver elements.
But they didn't use standard ultrasound materials for this.
No, they use this material called PVDF-TRFE. It's a gold-coated piezoelectric polymer.
Which is key because traditional probes use these rigid ceramics.
Right, and trying to build a massive continuous ring out of rigid ceramic would be a nightmare to manufacture.
Impossible. So this PVDF stuff, it's essentially a specialized, flexible plastic film.
And the piezoelectric part just means it converts physical pressure, like a sound wave, into an electrical signal.
Yeah, by using this flexible polymer, they can just contour the 512 receivers perfectly into this huge ring.
And then inside that ring, they have a single transmitter, an Olympus V395, with a custom diverging lens mounted on a gear that spins a full 360 degrees around the subject.
But the way they actually use this ring is, it's pretty unique.
Okay, yes, I have to admit, reading the methodology, I was laughing. It sounds so retro.
The dumb tank?
Yes. The human volunteer literally strips down to a swimsuit, climbs a little ladder, and sits on a stool inside a warm water immersion tank. The water comes right up to their neck.
It sounds like a sci-fi experiment from the 1950s.
Exactly. They hold their breath for 10 seconds to stop their lungs from shifting, and this motorized gear physically spins the transmitter around them in the water.
I was thinking, with all this advanced polymer hardware, why are we dunking people in vats of water?
It looks funny, but it's an absolute physics necessity. Remember that acoustic impedance mismatch?
The brow wall. Air is the enemy.
Right. If there is even a microscopic layer of ambient air between the transmitter and the skin, the sound waves will just bounce off. They won't even enter the body.
But water has an acoustic density that's very similar to human soft tissue.
Exactly. So the water is the perfect acoustic coupling medium.
It's basically doing the exact same job as that cold, slippery gel that technician squirts on your stomach.
Right, but scaled up to surround your whole body. It bridges the gap perfectly without any physical object pressing against your skin to distort things. I mean, the paper does note they don't expect future clinics to just have swimming pools everywhere.
No. Future iterations will probably be like a horizontal bed with a flexible water pouch and some gel.
That makes sense. But for this proof of concept, the water tank gives them the pristine environment they need to prove the math works.
And the math is where it gets incredibly cool, especially for the ML engineers listening.
Right. Let's get into the signal processing leads. To image a full cross-section, you have to punch through about 35 centimeters of tissue, fat, and organs.
Which requires a massive amount of acoustic energy.
But you can't just blast a patient with a huge, loud sound pulse.
Yeah.
The FDA has very strict safety limits to stop tissue heating and cavitation.
Yeah, cavitation is when sound waves literally create tiny, damaging bubbles inside the tissue. You do not want that.
Definitely not. The FDA limit for what they call the mechanical index is 1.9. But the Caltech team operates way down below 0.2. It's incredibly safe. So how do they penetrate the torso with such a weak signal?
They use something they call a chirp hack.
Right. Instead of a short pulse, they send a 400 microsecond chirp signal that smoothly sweeps in frequency from 0.3 to 2.0 megahertz.
It's a brilliant workaround. It's all about optimizing the signal-to-noise ratio without breaking peak power rules.
Because if you use a sharp crack of sound, you're limited by how loud that one crack can be.
Exactly. But a chirp, think of it more like a whale song instead of a gunshot.
Oh, like that.
By stretching the signal out over 400 microseconds, you're pumping a massive amount of total energy into the body over time, but the peak amplitude never crosses the safety threshold.
That makes sense for getting the energy in, but here is my question when I read it. If the sound going in is long and sweeping, wouldn't the echo coming back also be this long, blurry, smeared-out mess?
That's the intuitive problem, yeah.
Like if you're trying to measure a tumor down to the millimeter, how do you get a sharp image out of a smeared wave?
They fix it mathematically, using cross-correlation.
Okay, walk us through that.
So before the patient even gets in the tank, they run a baseline scan with just the water. This gives them a pristine recording of exactly what the chirp sounds like as it leaves the transmitter and hits all 512 receivers.
Unobstructed. So it's basically the acoustic fingerprint of that specific chirp.
Exactly. Then the patient gets in, and those 512 receivers record millions of messy, overlapping echoes bouncing off the liver, the spine, the fat.
And then the software takes that pristine fingerprint and mathematically sweeps it across the messy patient data to find exact matches.
Right. It's like having software listen to a noisy crowd to isolate the exact voice of one person.
That cross-correlation effectively compresses that long whale song back into a microscopic, sharp digital pulse in the data.
Yeah, so they get the deep penetration of a high-energy wave, but the mathematical sharpness of a tiny, high-res pulse.
And because they capture this from all 360 degrees, they aren't just getting a standard black and white picture. They extract 3 entirely different maps from a single breath hold.
Which is huge.
First is reflectivity, where the physical boundaries are. Second is the speed of sound, which tells you tissue density, because sound moves faster through dense muscle than loose fat.
Right.
And third is the attenuation coefficient, measuring exactly how much of the signal is absorbed by the tissue.
And this is where the AI community really needs to pay attention. Extracting those 3 maps from 512 sensors across thousands of positions is an immense math puzzle.
Yeah, calculating the exact microsecond time of flight for sound bouncing off a kidney and hitting 512 different receivers at different times, it's heavy compute.
Right now, using a 2D delay and sum algorithm on an NVIDIA RTX 3070 GPU, it takes about 12 minutes just to process a single anatomical slice.
12 minutes for one slice. That is a massive, glowing target for machine learning optimization.
Exactly. The physics and hardware are solved. The bottleneck is the matrix math. Training deep neural networks to reconstruct these acoustic fields in milliseconds instead of minutes is the next step.
And once AI solves that compute bottleneck, the medical applications are disruptive. Which brings us to the first real-world application they tested, high-fidelity adipose, or fat tracking.
The clinical demand for this right now is astronomical.
Because of all the GLP-1 weight loss drugs, right? Doctors need to know if a patient is losing fat or dangerously losing muscle.
Right. And the experiment they ran was fascinating. They used traditional skin fold calipers on a subject, where the doctor literally pinches your fat with a little tool.
Sounds fun.
Yeah, well, the calipers measured a fat thickness of 1.9 centimeters, but then they ran that same subject through the ultrasound tomography system.
And the scan showed the true thickness was actually 3.2 centimeters.
A huge discrepancy. Calipers severely underestimate the total fat because they only grab what can be physically pulled away from the muscle.
Right. It's like trying to guess the thickness of a mattress by pinching the top bedsheet. You're completely missing the compressed volume underneath.
Exactly. And right now, if a pharma company wants accurate internal fat tracking over a 6-month trial, they have to use MRI or CT scans.
Which means MRI is super expensive and slow, and CT involves ionizing radiation, so you ethically can't scan people constantly.
But this ultrasound system is radiation-free and structurally accurate.
And it's not just for weight loss either. They point out how crucial this is for tracking malignancies like liposarcomas.
Yeah, those tumors grow deep inside the fat tissue, sometimes up to 25 centimeters.
Because the system is completely safe, an oncologist could scan a patient every week to see if the tumor is shrinking from chemo. You could never do that with CT scans.
No, the radiation dose would be way too high.
So it does big structures beautifully. But the second major application is almost the exact opposite. It's about finding something microscopic.
The biopsy needle problem. This is brilliant.
It really is. It's one of the most elegant hardware hacks I've ever read. Yep. So the current problem. A doctor needs to guide a long needle deep into your tissue to grab a sample of a mass. They have two bad options.
Right. Option 1 is a CT scan. Insert the needle, leave the room, blast the patient with x-rays, check the image, adjust blindly, step out, blast them again.
Slow and radioactive. Option 2 is standard handheld ultrasound. But that only sees the needle if the flat metal shaft is perfectly perpendicular to the sound wave.
Yeah, if the doctor angles the needle even slightly to, say, avoid an artery, the sound bounces off at an angle and misses the probe entirely.
The needle literally turns invisible on the screen.
You're basically flying a surgical instrument completely blind inside the body. The margin for error is awful.
So the Caltech team's fix for this. They didn't reinvent the needle. They just took a standard, off-the-shelf commercial biopsy needle, and they clamped a tiny ultrasonic transmitter to its plastic handle.
And they pumped that exact same frequency-sweeping chirp signal directly into the plastic.
This is where the acoustics just play out so beautifully. Sound travels differently through different materials. By pumping it into the handle, they turn the solid stainless steel core of the needle into an acoustic waveguide.
Right, the sound races down the metal shaft much faster than it travels through the surrounding human tissue.
It completely bypasses the flesh until it hits the very tip of the needle. And because the tip is sharp and pointed, the sound doesn't shoot straight out like a laser. It scatters isotropically.
So isotropic scattering, right? It basically means the sound just explodes outward in a perfect 360-degree sphere right at the tip.
Deep inside the patient's body, the tip becomes a microscopic point source of sound.
Exactly. And because the chirp originates from that exact tip, the 512-element receiver ring in the water tank picks up that signal perfectly, no matter what angle the doctor uses.
The software pinpoints the origin of that chirp, tracking the needle tip at 30 frames per second, overlaid right onto the anatomical cross-section.
It's essentially real-time, radiation-free, 3D GPS for the surgeon's instrument.
Think about surgical robots. Having closed-loop feedback on exactly where your cutting tool is without exposing everyone to x-rays, it's a total game changer.
It really highlights the ultimate value proposition here when you compare this to an MRI.
Yeah, MRI can take up to an hour. This takes 10 seconds. MRI needs a massive superconducting magnet. This just needs a tank of water and some polymer sensors.
And because there are no magnets, it's completely safe for people with pacemakers or metallic implants.
Right.
Plus, zero ionizing radiation.
Cheaper, faster, safer. And this brings us back to why the AI community needs to care.
Right, the data sets for personalized medicine just don't exist yet. We don't have longitudinal data sets mapping the millimeter by millimeter changes of an organ over years.
And this hardware is going to generate the data needed to train those next-gen predictive models. But, and this is a slightly daunting thought to leave you guys with, what happens when whole-body ultrasound tomography becomes as common as checking your blood pressure at a pharmacy kiosk?
That's a wild thought.
Right. We're talking about a future where high-fidelity 3D acoustic blueprints of your internal organs are generated rapidly outside of a heavily regulated hospital.
Privacy implications are huge.
Exactly. What are the cybersecurity risks when a digital open-source schematic of your internal biology is sitting on commercial servers? If diagnostic power shifts into the home, how do we handle the privacy of our most intimate structural data?
It's an incredible breakthrough, but yeah, the digital footprint is something we've never dealt with before.
Totally. Well, thank you for tuning in to this deep dive on AI paper slop. Just something to think about the next time you hear a sound echoing down a hallway. That same simple physics might just be the key to lighting up the human body.